maybe let's go ahead and get started as people are rolling in. So welcome everyone to our final astrophysics seminar of this semester. We're very happy today to have our very own Eric Ford. Eric did his PhD locally at Princeton and was a Miller Fellow at Berkeley and a Hubble Fellow at the CFA before becoming faculty at Penn State, where he is currently on sabbatical and visiting, quote unquote, IAS. And we'll hear today about characterizing the architectures of planetary populations with Kepler and next generation Doppler surveys. And let me mention right now that following this talk this afternoon, we'll hold a group discussion with Eric at 3 p.m. And that'll be at the same Zoom link for anyone who wants to join. All right, Eric, take it away.
Thank you. So as Susan mentioned, I'll be talking about the prospects for characterizing planetary populations. It's roughly 3 parts. We have the part that's basically in the late stages of finishing papers about planetary architectures derived from Kepler. But since there's a crowd from many backgrounds, maybe it'll be useful to discuss some of that. And of course, that could fill up as much of the discussion as we want to do. And then hopefully I'll have some time to also talk about some of the work that I'm working on this year while on sabbatical. And a lot of that focuses on trying to advance extremely precise radial velocity surveys and a little bit of thinking about the future. So not just the current generation, but the next one. So what we do have a lot of data about is the demographics of interplanetary systems, and that comes from Kepler. But before I sort of dive into actually showing you results, I think it might be useful to take a slight philosophical digression and think about seismologists, so people who study the Earth's interior. And I find it kind of fascinating that in 2020, you'll still see papers and talks referring to PREM, or their preliminary reference Earth model. Now, obviously, in the last 40 years, they've made substantial progress. But nevertheless, they still find it very valuable to make comparisons to this preliminary Earth reference model, whether it's for interpreting new data or for interpreting their models to understand the deviations from a fairly simple but nevertheless pretty good model. And so with that sort of inspiration, we can begin to think about what would be needed to make a similarly useful preliminary reference exoplanet architectures model. And so that's sort of what motivated this SysSim project, short for Planetary System Simulator Project, that myself and Darren Ragazine and several graduate students have been contributing to over the past several years now. The basic idea is classic astronomy. You have a forward model. The sort of one interesting thing here is the forward model includes several different steps. So the first one is the physical description of what's the distribution of planetary systems. Then there's a model for how you go from that model to generating discrete planetary systems. So you get individual systems. You don't observe a continuous distribution. And then we have to simulate the Kepler observation mission. That includes both sort of inevitable geometric effects as well as some not so inevitable, but in real life, that's what happened effects. And so we try to make that simulation process as realistic as practical. And then we can compare the observed catalog from Kepler to the simulated catalogs coming out of our simulator. And then, of course, those models that are able to reproduce it well, we put a little star next to and remember, and the ones that didn't, we throw out and proceed to move on. And so this approach has been taken by several different groups. Oftentimes, the whole problem is pretty complex. And so I think one of the things that distinguishes ours is we've tried to do the inference on a lot of parameters at once. And that allows us to worry about some of the potential correlations that can bite us. So the goals for this project have been to characterize the distribution of planetary architectures, but also to understand the limitations. And so unfortunately, as great as Kepler was, there's a finite number of planetary systems that were observed. There are these detection biases, and that does lead to some remaining uncertainties. So we want to understand what are those uncertainties, and that way we can inform planet formation theory, but not over-inform planet formation theory. And of course, the shortcomings, the gaps in our knowledge that remain, that's what we want to think about for what should we do in future surveys so as to elucidate those questions that we weren't able to address with Kepler. So some of the features of the Kepler data are relatively easy to model. I mean, of course, we can obsess over all the details, but something like the distribution of orbital periods or transit duration ratios, they're fairly uncoupled from other questions. There's one parameter that sort of is dominant in affecting them. And so it's relatively easy, and lots of groups have gotten similar results. And so this has given us things such as the occurrence rate as a function of size and orbital period for planets. And now I think that's under pretty good control over at least the vast majority of parameter space. You might still see some concerns in the bottom right here, where you have sort of pushing the limits of Kepler, but even there we've seen significant progress in agreement among recent studies. But some properties are hard to model, and I don't need to read all the text to you, but I'll sort of jump into one of those right away. And that is, if I want to ask a fairly basic question, like how many planets are there per planetary system? Okay, maybe I restrict it a little bit because Kepler is only sensitive to interplanetary systems. Okay, can we answer that question? Here I just picked 4 studies and show 4 histograms for the inference for the number of planets per interplanetary system. And what you see here is that there's quite a lot of variability. And even if you pick our own one to the right here, you can see that with 2 different models, we get 2 different results. And so that tells you that it's not just different authors doing something different. There really is something in the model that needs to be resolved here. So why is it that different studies find different numbers of planets per system? And there's several effects that come into play, but one that's particularly important to appreciate is if you look at the number of planetary systems that have a detected number of transiting planets, on a log plot, it may look pretty boring, but if you kind of start at the right edge here, let's get right edge here, where you have a few planets. As we go from 6 to 5 to 4, the rate roughly increases by a factor of 4 or so to 100. And then as you go from 2 to 1, it sort of like shoots up much more rapidly. And so what you see there is that there's a excess of single planet systems relative to what you would predict naively from looking at the multis. Sometimes this is referred to as the Kepler dichotomy, if you've heard people referring to it. I'm not thrilled about the name. The name sort of suggests that maybe there must be some physical dual population. That's one possibility, as we'll see, but that's not the only possibility. But nevertheless, it's sort of the de facto name people are using to refer to this large number of apparently single planet systems coming from Kepler. So why? Oh, yes.
I have a question. I didn't quite understand what the problem is here.
So if I take the multiple planet systems and I say, oh, I can fit a model to describe these multiple planet systems, and I take those systems and I say, okay, well, how often should I see those multiple planet systems as a single planet system? Then I predict dramatically fewer planets observed as a single than there actually are. And so there's a factor of 2 or 3 more singles than quote there should be if you assume that the population we see as multiples is also responsible for the singles.
What assumptions go into this mental calculation?
Well, it's a lot more than a mental calculation. I guess for the talk purposes, I was trying to leave it relatively simple. There's many effects that go into it, and that's one of the reasons it's tricky. I think that the 2 dominant features that sort of enter in here are, intrinsically, how often do you have multiple planets? So how often are there 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 planets in your system? And then the other really key parameter is what's their mutual inclinations, right? Because if you have a system that's perfectly coplanar, then anytime you see one planet, you'll see all the inner planets to it. I guess modulo against signal to noise and detection issues as well for the signal to noise based on their size, but at least they'd all transit. On the other hand, if you have significant mutual inclinations, then you might see one planet but not the other. And for small mutual inclinations, there's a good chance you'll see multiple planets, but for large mutual inclinations, pretty rapidly it sort of becomes like n single planet systems depending upon where you view it from. And so a variety of studies have tried to model the multiple planet systems. In order to get so many times you see 4, 5, 6 planet systems, well, you need the systems to be very nearly coplanar. And then you say, okay, what if I take that same assumption for coplanarity and I then put it to all my systems? And then when you come here and you look at what you predict for the singles, then you sort of underpredict them by about a factor of 3.
So if I just say the Kepler dichotomy means that the observation is that there's a lot more stars with one planet than 2 planets. Is there any content more than that?
Yes, there is, because if you take all the stars you need to explain the multiple planet systems, and then you say, okay, now let me try to take all the remaining stars and give them 1 planet, you don't have enough stars to go around. So in the early days, there was this thought that maybe a simple explanation for this was you just had a lot of stars with 1 inner planet, maybe planet scattering cleared out most of the interplanetary system. But once we've understood our detection efficiency well, we can now see that because these multiple systems are very rarely observed, you see all 4, well, this means you need a lot of your stars to go to the multis, and then there aren't enough stars to give you just 1 because these you very rarely see because of transit geometry. And so you really need some of these singles to be multiples that aren't so well described by this single population of multiples out there.
Okay, well, I'm totally confused, but maybe you should keep going.
Okay. Well, so maybe I'll offer 2 explanations and then see if that helps clarify them. So one explanation that had been proposed from a variety of thoughts was maybe there's 2 populations of planetary systems, one of which has relatively low mutual inclinations, and by low here I'm talking 1-2 degrees as its typical mutual inclination, so even more coplanar than our solar system, and another population that has high mutual inclinations. And so that population would need to be high enough that we typically see them as single planetary systems. And so we can make this model work, and you get roughly 40% of the systems need to have high mutual inclinations. You might be somewhat worried that maybe the mutual inclinations are too high here in the model. What this really says is they're largely unconstrained. Once you get up to 20 degrees, whether they're 20 degrees or 40 degrees or 80 degrees, it doesn't really matter to Kepler because it just sees 1 of them at a time. So this was one model that could explain the observations, and this maybe sort of fits the narrative of Kepler dichotomy, or the language of it. And it's also not physically implausible. You could imagine late stage dynamical instabilities or secular perturbations from more distant planets causing the nodes of planets to become misaligned and stimulating some large mutual inclinations in the subset of stars that had either these external perturbers or late stage instabilities. But I don't want you to think that's the only explanation for why so many stars have a single transiting planet. There's a second scenario that involves saying that, well, maybe this idea of trying to assume that we learned everything about all stars from the multiple planet systems is a little bit misleading. And so in particular, early on, we assumed that all the multis were 1 population. We fit a model to them, and then we tried to extrapolate that to all stars. More recently, we said, well, what if there's a correlation in particularly the mean mutual inclination among planetary systems with the number of planets in that system? And you can imagine this could arise pretty simply from planet formation just because of dynamical stability. If you want to cram in 10 planets in your interplanetary system, they're going to need to have low eccentricities in presumably inclinations so as to fit and be dynamically stable. Whereas if you only had 2 or 3, they could be more widely spaced, have larger inclinations and eccentricities. And so a few studies have looked into this population, this sort of scenario, where instead of positing 2 physically distinct populations, we say, well, there's really 1, but there's this interesting correlation with the properties of the function of multiplicity. And if you do this, we can also explain many of the observed phenomena, not just the number of stars with each number of planets observed, but also the sort of key 1 and 2 point summary statistics about the multiple planet systems. So maybe I should pause here and ask, did that help resolve any of the questions from Roman and Scott?
Not to me.
Not to me.
I still don't understand it. I mean, this is just a formation question, isn't it? I mean, like, how many planets does a system have? So I don't really see what is a problem here. I mean, it's just an observation that you're making.
So I like the way you phrased this, not as a problem. You know, it's like paradoxes, right? Paradoxes aren't really paradoxical. They just illustrate the shortcoming of your understanding, right? And so in this way, I like thinking of the Kepler dichotomy as an observation that there's a whole lot of stars with one transiting planet, and that if you try to explain the singles purely as a result of those multis which you just happen to view a certain way, the simplest of models don't work. But you can solve it. You don't need to play ridiculous games with like, oh, there's 40 planets or something. And in fact, even those don't work if you don't introduce some of these correlations. But rather what it says is that in order to explain the high rate of single planet systems relative to the doubles, triples, quadruples, and etc., you either need to have two populations, or you need to have mutual inclinations, or you need to have a correlation in the mutual inclination with planet multiplicity.
So in this second scenario, many of the single detection systems they do actually have multiple planets, but it's a small number of multiple planets and therefore high mutual inclinations.
Yeah, let me see if I can find that figure quickly. So here's the intrinsic multiplicity of those two models.
Okay.
And so I was going to sort of talk about this in the context of what radial velocity surveys might see, but it might help to compare how many planets are actually between 3 and 300 days in these systems. And so the two population model in blue here shows you have a lot of stars that have no planets. And of those that do, they typically have 4 or 5 planets in this 3 to 300 day range. And then some of those are low mutual inclinations and explain the multis. Some of those have high mutual inclinations that explain the singles. But that's not the only scenario. The other alternative where this correlation, we can have a distribution where now 80% of stars have at least one planet in their interplanetary system, and the mean number is only 2 or 3. But there is a tail that goes out to higher multiplicity. And as you go to these higher multiplicity systems, now in order to explain why do you see so many 4, 5s, and 6s, well, those need to be very well aligned in order to have a high probability of seeing them as indeed a high multiplicity system.
So am I correct if you say the simple model is that all systems have a single Rayleigh distribution of inclinations, and it's the same for all systems, that model is inconsistent with the data?
Exactly. Right. So that was an example of some of the early models that were invoked to try to explain things. At the time, we viewed those as plausible because we were concerned that some of these single transiting systems might just be some sort of astrophysical false positives. And when we didn't know what fraction of these were real planets, we were concerned about it and said, well, maybe there is just one set of planetary systems with a single Rayleigh distribution that worked. But then as we became more and more confident in the high fidelity of the single planet systems, that was no longer good enough to explain the data. And so then we had to invoke something to go beyond that. And whether that involved a second population inclinations or this correlation inclinations were the two models that I think are the most compelling to explain this.
So even if you cannot see in these models where you have a lot of unseen companions because of the inclination, even you cannot see those, maybe you can see their perturbations on the orbits of the ones that you have. Is that?
Yes, there are select cases where we're able to recognize the dynamical effects of the planets, or maybe really kinematic in most cases, dynamical and even smaller fraction. Though that population is small enough, and also the selection effects are hard enough that while some people have made early attempts to make use of those, I think it's still early in the game for there. So I'm going to put those in the category of areas for future research. So for example, two of the studies that I mentioned here that assumed analytic correlations in the multiplicity. So the Yang study in purple and the previous Zhu study in sort of a yellowish orange. They attempted to kind of look at how often they saw planetary perturbations and use that to make an estimate for this power law that they fit to the data for intrinsic planet multiplicity. And then they took that as fixed and used that in the rest of their modeling process. In our case, we did not sort of put that in, but rather let that emerge as a result of the stability constraint and the mutual inclinations. And we're able to see that when we put in systems that are dynamically stable in a long-term secular sense, we're able to sort of get out a prediction for how this inclination correlation should fall if systems are sort of near their threshold for instability due to the formation process exciting them.
So Eric, can I sort of interpret my reading of this histogram that you showed that when you called it the Kepler dichotomy by just saying that so these observations of singles cannot be explained by any geometric effects, and so there is a certain number of stars which really truly have just a single planet around them. Is that
no? So that's what I want you to reject. So early on, we wondered about that, right? Because early in the process, our understanding of Kepler's detection efficiency wasn't mature enough that we were able to make firm statements about how often we saw a single transiting planet that it was real. So early on, I was like, oh, maybe we could just sort of tweak all the distribution of actual planets so as to get out this result. But as we sort of begin to get a better understanding of the detection efficiency, we can see that no, we can't explain the single planet systems by just dialing up the number of stars with one planet, because if we do, there aren't enough stars to explain the multis. And conversely, you can't just try to explain, say, the number of high multiplicity systems by making sort of like 100 planet systems or something, because the stability prevents the very high multiplicity scenarios that you would need to explain this with sort of 20, 40 planets or something per system. And so we now are able to say that we can model the distribution of number of planets per system as a variety of possibilities that involve either some fraction, let's see if I come back to this figure, some fraction of stars having high multiplicity systems and roughly half of stars having no interplanetary system, or fewer planets per system, but a much broader distribution. Of course, if I tell you that both of these models work, then the linear algebraist in you should realize that you can also take any linear mixture of these two models and also reproduce the observations. So these are sort of designed to be end members of ways we might be able to explain the data. And so somewhere between 80 or so and 50 or so % of stars need to have an interplanetary system, but exactly where it falls in that is sort of degenerate with this question of how large is this second population of high inclination, highly excited systems. And if it's large enough, then we might only have 50% of stars having an interplanetary system. If it's non-existent, then we need to drive up the fraction of stars with planetary systems to be over 80%. So perhaps another point that might be a little bit reassuring about this is, in constructing these models, we looked at basically a lot of one-point statistics. So we looked at what's the distribution of orbital periods, transit depths, transit durations. And then we went to the 2-point statistics, things like the ratio of orbital periods, the ratio of planet sizes or transit depths, the ratio of transit durations. And so those were the things that went into our initial set of models. Subsequently, some people have pointed out some higher order effects, sort of statistics that can be useful for diagnosing whether these models are on the right track. And so one of the things that causes me to place a little more credence in this idea that there's a correlation with multiplicity with inclination is one thing that we didn't put in the metrics we use to evaluate the models, but subsequently thought, we probably should have checked that, was how does the distribution of the transit duration ratio compare in systems where we see 2, 3, or 4 or more planets in the system. And so what we can do here is we can look at either the cumulative or here the histograms of these this model, and you can see that the 2 planet systems in red here have a relatively broad peak, whereas the 4 and more planet systems observed have a sharper peak near the middle, where the ratio of the durations is more close to that what you would expect if the planets were nearly circular and coplanar. Of course, not all systems are circular and coplanar, so we expect there to be some broadening, but this gives us a nice reference points because we can control for things such as the orbital periods that we measure very well, and that distribution tells us about the eccentricities and inclinations of the systems. Inclinations cause it to become skewed, eccentricities cause it to broaden out, and so we can tell that the eccentricities, inclinations of these 4 and higher systems needs to be a little bit smaller than for the 2s. Does it give us enough information to sort of pick out, this power law index or how it is? No, it doesn't. It's too weak there. But nevertheless, it's nice that this is something that was not placed as a constraint on the models, and nevertheless that the models that passed all the other tests also, in the case of this correlated inclination multiplicity model, also comes out sort of without trying. So that's another indication for this sort of correlation being there at some level. Okay, so maybe let me try another sort of direction of interesting observations, and that is correlations with the planetary system. We talked about this mutual inclinations, but there's other things as well: planet sizes, orbital periods, planet masses, ordering, and some higher order effects. And so the short version is the nice thing to do would be imagine planets as a Poisson process, right? Where you sort of say every planet, knows nothing about, just has an equal probability showing up everywhere. And we tried that because it's easy, and lots of the likelihood-based methods use that assumption. But if you do that, if you look at things such as the orbital period ratio distribution or the transit depth or the planet size distribution, you're not able to model the results with those distributions. And so instead, we're driven to models where we allow for correlations between the orbital periods within a system and also the sizes of planets within a system. And so this can get fairly tricky to be exactly what you mean. So there was a nice paper recently by Merchikova and Tremaine that kind of tried to help clarify some of these. Interestingly, what our model does wasn't any of the sort of cute descriptions they gave, but rather something in the middle that's not as simple. But so in our case, it's the planets in every system. They know about a latent process that tells them you're in a cluster with a certain characteristic orbital period and size. And so what that's saying is that most of the time when Kepler sees a planetary system, it's only seeing planets from one cluster. They have very similar orbital periods and sizes, but every now and then it sees planets coming from 2 clusters that typically have more disparate periods and also sizes. And so this sort of clustered model allows us to build in some of the correlations that are needed, but also not require that all planets in a system sort of be too similar, but allow for the longer tails. And so that's sort of an interesting observation that we can now see planet formation is creating. Did I hear a question?
Yeah, so in your figure on the right, in your top right panel, should I conclude, does your model actually favor something where it's smaller planets closer in and larger planets further out, or that's just one particular example?
Yeah, that's one example here. The current model doesn't discriminate across clusters in the sense of every cluster gets a characteristic orbital period and characteristic orbital planet size that are drawn independently. So in this case, the latent process describing the properties of the cluster is now a Poisson process. And so they're independent, but then within each cluster, the planets know about each other. Now, if you ask me what's really going on, I actually think you're right. There appears if we look at some of the higher order statistics, let's see, did I think I left this one out. But if we look at some of the higher order statistics in what our model doesn't do well. So in other words, we put in this model and look for features about the correlation between the size as a function of its ordering. We can recognize that we're not quite getting this right, and there's a preference for the more distant planets to be larger. And of course, that's tricky because more distant planets are harder to detect, and so you'd worry about detection biases. And so one of the nice things about this model is even when our forward model isn't sophisticated enough to include the more distant clusters having a larger characteristic size, we can still kind of do like a null hypothesis test where we say, well, let's take our model as the dumb version, fold in all the selection effects and see, yep, there is a preference for it to detect these more massive planets in the exterior, but it's not as strong as what's observed. And so the excess strength of the correlation is beyond what the detection effects lead us to believe that there actually is a preference for the more distant planets to be larger. So that was sort of a quick summary, maybe in retrospect a little too quick, of some of the interesting things that we're able to learn from architectures and Kepler data. And of course, this naturally leads us to like, what are the limitations? And so we sort of at the end, we're discussing some of these higher order statistics, things like how uniform is the spacing in multiple planet systems that we're starting to sort of look at how we can do better for. Also, someone, I forget, asked about whether we could recognize the interactions, maybe Matthias. And so the transit timing variations due to planet-planet interactions, or the transit duration variations due to orbital precession provides information about that. And so we're starting to try to incorporate that information as well. But then the one I thought I'd emphasize today is radial velocity surveys, because obviously they're the other big piece of information we have. Traditionally, they've been difficult to interpret because there's a little bit of astronomers liking to chase shiny objects. But sort of as we sort of are starting to have an increasing number of planets, it's more and more realistic to look at things like, could we do a systematic follow-up program? Or could we do fresh new surveys that aren't as biased as previous ones? And so that sort of motivates us to ask, could we discriminate between these different models for things like eccentricities and inclinations, assuming that inclinations or eccentricities are correlated based on just formation grounds, then these two models for the inclination distribution are likely to have different eccentricity distributions, and that's something that a radial velocity survey could pick up on. Another thing that's sort of interesting is, as a dynamicist, I'm always the most interested in these multiple planet systems because there's lots of things I can measure and try to fit and look for interesting correlations and patterns. But if I take purely the sort of information theory version of myself and say, which systems should I follow up? And then compare these two different models, well, once I've seen 3-4 planets in a system, I already basically know this system is one that has low mean mutual inclinations. And I'm probably not going to learn a lot more about the mutual inclinations and find some surprise by finding the remaining planets that don't transit. On the other hand, when I see only one transiting planet, well, then these two models make wildly different predictions for how many other planets are in the system, right? In one system where the typical system had 5 planets, I see one, well, I still expect to find 5 or something more if I had a really good radial velocity follow-up program. On the other hand, if the reason for these high multiplicity systems is low mutual inclinations, well, just because I see one planet doesn't necessarily mean I'm in that regime. And so the typical number of additional planets is just a few. And so there's a sort of scientific reason to try to conduct follow-up programs of systems where you see just one transiting planet. And further, we can then say, well, if we condition on the number of planets that we observe and sort of then look at the system, how does that affect things? And so it's useful to sort of first look at what's they're in the intrinsic number of planets. So here I've showed panels going from 1 planet per star at the bottom to 10 planets per star at the top, and looking at what the correlative model predicts for the eccentricities in the middle column, the inclinations on right. And so you can see we predicted as you get to higher multiplicity, you have lower and lower eccentricities in the system. That's something that radial velocities could detect fairly well. But also there's some interesting, because the correlations, if I look at the period spacing, there's also some pretty big differences. So if, for example, when I have a multiple transiting system, that often has planets that are spaced by period ratios of 3 to 2, because there's several closely spaced planets, maybe up to 2, and not many much beyond that. And so these systems where I have multiple transiting planets, I'm typically in this regime where I have relatively low eccentricities in either model. But once radial velocities come along and allow me to find planets that are spaced by a factor of 4 or 5, well, now the predictions for the eccentricities of those additional planets is quite disparate between these two models. And so the ability to find planets that are more widely separated and then study their eccentricities will also be a good discriminator for these models. I wasn't sure if I heard someone trying to chime in there. Okay, so that's some of the things that are at least possible in theory. What's possible in practice? And so the Transiting Exoplanet Survey Satellite, TESS, has been conducting a full sky survey or near full sky survey to find similar targets, but now aiming at brighter stars. So unfortunately, the time baseline is much shorter, so we typically don't find as high multiplicity systems as nearly as often, but they're now well suited to follow-up observations at ground-based observatories. So one thing you can ask is, based on what we've learned from Kepler, what do we expect to be out there when we see one transiting planet? And here we sort of conditioned on there being like one planet between 5 and 10 days that's detected via transits. What's going on? And so on the right-hand panel, you see the RV signature of, in red, the planet that we conditioned on being in the system, and then in black of the total system. And so sometimes these are quite similar. And if you were to conduct follow-up observations, you would measure the planet that you saw in transit, and you would measure its mass, and you'd be happy and move on. But other times, you might think you have an orbital period that you want to phase fold your data at, but the RV signature you see is coming from other planets. And so, you might have had a strategy, I'll get 10 data points at the phases where I have the maximum minimum velocity. And when you do that, you just either fool yourself and are confused, or you realize that the better scenario that, hey, there's something else going on here.
So on the left, these are just random draws from your model?
They're random, but we conditioned on there being one transiting planet between 5 and 10 days. Okay.
But right. And the things being shown are the non-transiting planets.
I think there's some system of red circles indicating which ones are not transiting, and the ones without a circle are transiting, and so you can sort of see that all the planets in the system are shown, but then on the right, the red shows the RV due to the planet that you were sort of imagining you saw in transit and wanted to follow up, and the black shows the RVs of the full system.
So Eric, this is not the data, right? This is not the real data.
Right. No, there's simulated systems coming from our population simulator.
Also, I hope the telescopes that you showed are then not simulated either, because this is a bit confusing, to show telescopes and then simulated data.
Oh, well, the point there was that there's a whole lot more instruments. So TESS is finding planets around bright stars, which are amenable to smaller telescopes, and there's an increasing number of instruments that are capable of following them up. And so now there's something, whereas in old days there were kind of two groups, now there's just so many more of them that Magellan and Espresso and HARPS North and NEID and Express, and so there's a lot more follow-up activity capable of going on, and so we're going to be able to follow up many more systems than when we were in the Kepler regime. So the Kepler was great, but the targets typically faint, and we were sort of overloaded because they're only up so many months a year, and there were only so many telescopes that could follow them up. And so we were really limited in the RV follow-up. And so nearly all the Kepler science came from looking at Kepler itself, and a relatively small number of papers based on getting RV follow-up of them. It was a major effort. It was great work, but it could only do a very small fraction of Kepler systems. And the point of TESS was to change that. And so now radial velocity is imagined to become a much bigger part. And so the first caution here was that if you say, oh, I want to take my transiting planet to the telescope and characterize it, you better be careful, because oftentimes the planets you learn about are not necessarily the planet that you saw in transit. And that's sort of a key lesson from the Kepler systems. Another question you might ask is, if I imagine there's a planet, again, here I picked 5 to 10 days, and I say, well, where are those other planets, and how do their amplitudes compare to that of the transiting planet in terms of RVs? On the top histogram here shows you the period distribution relative to the period distribution of the planet that we conditioned on. So most of the time the planet's exterior, but sometimes it's interior. And then the vertical axis shows you the distribution of the ratio of their radial velocity amplitudes. And if anything, the mean is slightly larger for the largest other planet being larger than the planet that you're sort of trying to follow up in transits. And so what that means is that typically you should be prepared for there to be at least one other planet sort of confusing your follow-up observations. And so what this means is you can't sort of have the minimal follow-up strategies, but rather you need to have enough observations to disentangle the other planets contributing to the radial velocity signature and separate the contributions coming with the orbital period that you're trying to follow up if you're, say, trying to measure a mass and a density. The good part is, now that observers basically have to do this, they'll be learning about those extra planets in the system, and that will be very exciting for those of us interested in multiple planet systems. So coming back to the sort of dramatic improvement in the radial velocity game, I think a lot of the lore sort of stalled at 1 meter per second precision for a long time, but now there are instruments that are pushing below that. So in the infrared, HPF is now getting 1.5 meters per second for real stars. In the infrared, near infrared, which was way better than what you'd heard before. Express and NEID, in the most favorable cases, you're seeing precisions of 30-something centimeters per second. And so that's exciting to see that now the instruments are capable of doing much better. But as the instruments have improved, that sort of raised a new area of concern, and that is that the stellar variability is the limiting factor for most stars. There's sort of a couple of effects. Yep.
So, I mean, why do you need to go to such high RV precision if, this simulated data that you showed before, they had like kilometers per second, right?
Meters.
Sorry, can you go back?
Yeah, so those are all meters per second.
Oh, it's meters. Oh, I see. Okay.
Yeah. Kilometers per second is great for studying binary stars. Meters per second is pretty good for studying super Earths, mini Neptunes that are close in. But if you want to go to either sort of Earth analogs, even close in, but especially if you want to push out to longer periods, then Earth is 9 centimeters per second for the sun. And so there's a big push to try to reach that goal so that we can find Earth-sized planets. But the good part is the instruments have now progressed to the point where they have higher precisions and are allowing us to see things that aren't before. But I think equally and perhaps more important is the degree of stabilization. And so HARPS could get great photon noise, but the degree of stabilization of the instrument has sort of been upped as we go from HARPS to Espresso, NEID, and Express. And so now we're able to control the instrumental effects, and that allows us to make use of new information that previously we were sort of scared to use because we knew a lot of it was instrumental variability. So perhaps the easy type of variability to think about is star spots. There's been a lot of study that already. Perhaps the scarier thing is convective flows, things like granulation, maybe even super granulation patterns. And the reality is that we're now detecting signatures like this, and that's going to be a challenge. Deborah Fisher made a great little graphic of, as you try to push towards the lowest precisions, anything you're not worrying about can come back to bite you. And so this sort of has led us to think about how are we going to distinguish planets from activity. And so the good part is for planets, you understand them very well. And so you know that there should be a persistent orbital period, amplitude, phase. It's purely a Doppler shift. Every line is doing the same thing. But stellar activity is going to be different. It won't be perfectly coherent. Line shapes can change, and there can be differences from line to line. And so what we want to do is to use these various discriminators to help us be able to separate what types of spectroscopic changes are due to planets and what are due to the stars. And so I think it's useful for sort of thinking about how this works to divide things into two regimes, the time domain and the wavelength domain. And we'll think about those, at least for now, separately. And so what this has really necessitated is a new generation of pipeline development for how we analyze these surveys. In the past, we took every spectrum, we measured a velocity, and then we published a nice little table of time, velocity, and velocity uncertainty. But now that's no longer good enough. Now we need to be analyzing not just the velocity, but also other properties of those spectra, which may be quite subtle. Maybe they're how the apparent velocity appears to change from line to line. Maybe it's the asymmetries, the line profiles, where the width of those line changes. And so we've been working on sort of going from fitting just one univariate time series to fitting multivariate time series, making use of things like Gaussian process models, where we have a latent Gaussian process that then explains multiple properties of the spectra all at once. And so this is work that right now it works beautifully on simulated data, and we're just beginning to start trying it on real data coming from either solar observations or expressed and hopefully soon NEID. In those simulations, we can use the time domain to distinguish between true planets and stars, because the true planets are persistent and the stars' variability is not persistent and shows up as this Gaussian process component being favored over the planetary component. If you this should be the last figure of another talk, but the short version is the red curve sort of shows what happens if you just pretend the star isn't variable, but you take a lot of really good observations, you might be able to get to a little bit better than a meter per second. The green curve shows what happens if you assume that there's sort of an excess noise, but it's uncorrelated noise. You assume you can't model it. And so you can do a little bit better there. And then the other curves show what happens as you try to start to model that, not as in a physical way, but in a mathematical way, saying I need a flexible function that can describe activity, but now I need to penalize that function, do a big Bayesian set of integrals to compare the evidence for models with a planet that has a simpler, more constrained model to those of a more flexible model for stellar variability, and then look at how often you're able to detect it, controlling for your false discovery rate. And we can see that, for our realistic models, we're kind of getting to 0.2 meters per second, so about twice the ideal world. This set of simulations was designed, so in the ideal world, it would just detect an Earth, and sort of our current time domain methods are making progress, but are still a factor of 2 or more short, and this is in sort of an idealized case. And so my conclusion from that is that the time domain alone is important, but it's not sufficient, and we will need to have more than just intensive, throwing lots of observing time at it. And so that motivates us to look at what we can do in the wavelength domain for how we can distinguish stars and planets. And so there's been several studies looking at the information content here showing sort of how much information you could extract from simulated solar spectra, even in these relatively simple simulations, looking just at spectra that include sort of linear combinations of resolved solar spectra to simulate spots. We can see that the current generation of spectrographs could get sort of one piece of shape information. If you just banged on the star with lots of signal noise, you get out 2, but getting to 3 or 4 is really expensive. The hope is the new generation of spectrographs with higher resolution will allow us to sort of get one more piece of information out of that. And in reality, the different mechanisms will each contribute different types of signals, and so the signals will probably be even more complicated than that. And so to test this, one star we do have very good data for is the sun. And so one thing we've done is we've made use of the HARPS North observations of the sun for a few years and tried to see how well we could remove the contamination due to solar activity in the case of that the sun, where we know what's going on. And so here's just stacking a whole bunch of cross correlation functions of the spectrum across a binary mask, and you can sort of see that there's little patterns. That's basically solar activity, mostly active regions. And we can try to decompose this in different components. Depending on how greedy or cautious you are, you might conclude there's 5 or 6 components. You might conclude there's 20. I sort of here chose to focus on the first few. And when we do that, we can recognize some features that are known astrophysics and some that are known instruments. And if you go beyond 6, you start getting into, we're not really sure what's causing it, whether it's some astrophysics or some instrumentation.
Sorry, we have a hand up from Sue.
Oh, great. Yeah, thanks for telling me.
Actually, Eric, this is from a little bit earlier in your presentation.
Sure.
My understanding is that the current limits on RV precision are about 30 centimeter per second, and even that can't be maintained for very long. So maybe I missed this, but did you address that? The current
well, so I think you're right in the sense, if I were to phrase it as what has been demonstrated by Espresso, Express, NEID, is that on short time scales, they're good to 30 centimeters per second. I wouldn't want to say that they're not good to that level on longer time scales. The hope is that things like laser frequency combs will provide long-term stability over many year time scales, but I think it's fair to say they haven't yet demonstrated that. And so I mean, Express probably is the longest baseline. They're, I think the best stars are maybe half a meter per second, so maybe 50 centimeters per second, of empirical RMS, but presumably some of that is the star itself. So I think we're in the regime where it's possible we really are at 30 centimeters per second for the surveys that are starting now.
Right, thanks.
But that's kind of the concern is that even if your instrument's good to 30 centimeters per second, if the star is dancing around at 3 meters per second, why bother collecting that many photons? And so the funny regime we find ourselves in now is we don't know how well we can do and what will be enough to get there, right? In the sense of to actually not just have the photon noise for an idealized star, but have the signal for a practical star. We need to be able to remove these stellar activity signals. And so what we're doing now is we're collecting data as if these problems can be solved once we have higher quality data, and then we'll see how well we do. And whether we'll be able to remove a bunch of stellar activity. And so on the encouraging side, even with HARPS North, which again is not as well stabilized as the other ones, we can see that we can get out about a factor of 2 from the observed solar variability during a relatively quiet time for the sun, from a little over 2 meters per second to nearly 1 meter per second, using only fairly simple wavelength domain techniques. There's a lot of room for improvement on this, but just our sort of our first pass. Other authors using very different techniques have also gotten similar levels. I think the best case I saw was maybe 0.8 something meters per second for a similar data set. You can argue about overfitting and such, but either way, we're making substantial improvement, a factor of 2 or 3 over what the sun is doing with existing data, and it's kind of the previous generation of instruments, and we're hoping the new instruments will allow us to do a lot better. And so here, maybe to illustrate the point of the calibration systems. So here's NEID's first light of 51 Pegasi back before the COVID shutdown. And you can see there's both this, the thing that looks like continuum with little lines, that's obviously the star, 51 Peg. And those dots show you our new calibrator. And so in this case, that's a Fabry Pro Etalon calibrator that gives us coverage across the entire range and can be done simultaneously with the observations. For NEID, you can also do simultaneous laser comb if that proves necessary. We're hoping it won't, just for logistical reasons. And so we were bracketing these Fabry Pro Etalons with the laser comb at the beginning end and maybe the middle of the night. And so now our wavelength, instead of being like wherever you happen to have thorium argon lines or wherever you happen to have iodine absorption lines, there are these like really beautiful, sets of calibrator sources. And so with the smoothness across your entire detector from these etalons, and with the long-term stability provided by the sort of intrinsic fundamental physics provided laser frequency combs, the hope is that we'll get this sort of 30 centimeter per second, not just from 3 nights of data that we can show it on now, but over longer timescales. I mentioned NEID because being at Penn State, I sort of have to advertise our own instrument. Unfortunately, I think it was this week I got that the COVID shutdown was now at the point where they were taking the first data since the shutdown ended at WIN, but it's engineering data, commissioning data. The commissioning got interrupted. So at the moment, my team is playing with data from the little solar feed off the top of the ancillary building here, and actually the data we're playing with comes from the parking lot of our at Penn State before we ship the instrument out. And so we're exploring things like how we can measure differences in the velocity for lines of different depths and different colors, and try to use that. NEID has a particularly large wavelength coverage, and so we want to use that to give us extra information about activity, showing a difference from the red to the blue of the spectrum. So this is work that's still in progress. That's what I'm working on now. So hopefully we'll make some good progress there. I'll probably go quickly through this, but I do want to say a little bit of some of the implications for future surveys. So direct imaging missions, HABEX, LUVOIR, whatever new acronym they come up with next. The early question was how big a telescope we build. Kepler has largely put those concerns to rest. We now can be confident that we'll find something. But there's this new question of when and where should it look? And you can show that if you had no precursor mission, you do a blind survey with these instruments, these mission concepts, you could find Earth analogs, but it would be much less efficient than if you knew which stars were good ones to look at in advance. And so this motivated NASA and NSF to put together a working group to consider, what are the limits of EV, or what's a plausible strategy, and could we have some fairly ambitious radial velocity program as a component or precursor to these direct imaging missions. And they sort of did some simulations that included things like the instrumentationalists weighed in on the limits of instrumentation, put in realistic distribution of where telescopes are, and cloud conditions at each site. And then we sort of got to dream big in terms of what telescopes we'd put there. So everything from 2-meter telescopes to, there was even one design of putting an ELT involved. That one I'm not going to show simulations for because it's a little bit silly. But the other ones where we envisioned 2, 4, 6, 8 to 10-meter telescopes, and looked at what could we do. And folding together the various sources of uncertainty. And the conclusion was that a variety of architectures could get enough signal to noise over a 5 or 10-year survey to measure the precision of Earth analogs with a signal to noise of well above 10 for a list of over 100 stars that were good targets for these direct imaging missions, if we could completely remove the stars' variability from the RV data. And so if you want to be an optimist, you can say, we could have failed. We could have shown it would be just infeasible to do that, even with, assuming we could solve the problem. If you want to be a pessimist, that's a fairly optimistic assumption about stellar variability. And of course, the working group also had people who are experts on stellar variability, making long plots of all the things that might go wrong. And of those, 2 that got a lot of attention were spots and granulation. And so something that we've been looking at recently has been what's the impact of that stellar variability, in this case on the signal to noise of masses. And so these histograms show in gray a simulation analogous to what this working group did, assuming that it was just a solved problem. You got back down to your photon noise. In blue assumes that we're able to remove the correlations, but there's still an sort of IID random noise that's left after removing those correlations. And the red assumes we make basically no further progress, that the methods we have now for removing stellar variability is as good as we do. There's correlated noise that remains, and you can sort of see what happens there. It makes a dramatic hit if you keep this signal to noise of 10. It really reduces what you find. Some people think that for purposes of characterizing planet atmospheres, a signal to noise of 5 is sufficient. We're imagining this being in complement with transits or direct imaging, so you don't need to worry so much about false positives. You're interested in how well you measure the mass. And so we broke this down by the source of what the source of variability is. Spots are the biggest one, but also perhaps the easier one to mitigate. The other one I find more scary is granulation, because it's going to be really hard to mitigate. It kind of produces a fundamental limit in terms of how well you can do. And what we showed is that because of granulation largely, there's actually a pretty big benefit to extending your survey duration to long time scales, because there you remove some of if you just take many observations in one night by throwing more telescopes at the problem, you don't actually solve this granulation. But if you spread out your telescopes over a longer period of time, your noise starts to become less and less correlated, and you can start to pull out a significant fraction of these, even at high signal to noises for Earth analogs. So that's the sort of half full, half empty, depending on how you want to go. There are more things, of course, we could talk about, but maybe I should throw it open to some more questions.
Great, thank you. Feel free to jump in or raise your hand. Sukanya.
So Eric, I guess this is a follow-up to what I asked earlier. I mean, a number of spectrographs have had laser frequency combs. Sorry, I'll ask you later. Sorry about that.
Well, okay, so maybe I'll guess. So you're right. Harps North had a laser frequency comb. They stopped using it. And so why was that? It's just for, there's a difference between having something that works in a lab with a laser physicist and something that you can use every night. And so as the technology's matured, we're hoping that now we'll be able to have these things operating, every night for years on end, as opposed to sort of a toy demonstration project, which was, exciting and compelling and helped lay the groundwork for the future generations, but what didn't become, say, a routine part of the HARPS observing cycle.
I see. Thank you. And that was very impressive. You managed to answer my question, even though I didn't fully.
Like Jeopardy, where you hit the buzzer before you hear the question.
Exactly.
All right. Do we have other questions? I know we've already asked quite a few during the talk.
I have a very naive question, if I may ask.
Mm-hmm.
So if about sun, like spots on the stars, is it possible at all that, if the star has a big group of spots, it can group and very concentrated group of spots, it can be confused with a planet?
Yes and no. So the good thing about spots is that, at least for the sun, that they come and go, right? And so if you took a short set of observations for, say, over a course of a week or two, trying to follow a transiting planet candidate, and that's all you had, then I'd be very worried with that, right? Because a spot group could persist for, a rotation period, a week or something. On the other hand, if you're imagining you're going to be observing a star for 10 years, now you're imagining there's, a spot that stays the same for 10 years. That's a much bigger ask in terms of how likely it is to be confused. There are some very active stars where you do see, persistent polar spots and things, but those are really big spots. And in the sun, we see that the larger spots have longer lifetimes and sort of decay times. The shorter spots have much shorter time scale. So I'm actually more concerned about the small ones. So right now we're typically thinking of, a 0.5%, a 0.1% spot that might contribute, a meter per second-ish of signal, because that's where our instruments have been at. And those are the types that might last for, approaching the rotation period of the sun. As you go to smaller and smaller spots that create signals of 10 centimeters per second, their lifetime is only hours. And so you can see the problem where if you had a spot that lasted 2 rotation periods, it would be annoying, but you could observe a 4 rotation period, see it came and when it went, and you could know when it was there, and you could know where it was, when it was on what part of the star, and you could apply a correction, and you could try to model it out. If you have a spot that comes and goes over the course of 3 hours, well, how are you going to model that? You're not. And so that's going to contribute more, nearly a white noise signal. And so I think the big spots, although they're the problems we faced in the past and are still kind of trying to overcome, in the long term, they're going to be the ones that we can model relatively well with some of these things like multivariate GPs, but the small ones are going to be the ones that are going to set our ultimate limit for what we can achieve.
And do we have stars which are really, really slowly rotating? Like
Yes.
How far do they?
Yeah, so there are some pretty slow rotators. I don't know the activity information for those. There's been some work on rotation rate and stellar activity, and of course, for young stars, there's strong correlations between the rotation rate and level activity. The really precision RV surveys, they're going to try to avoid those. And so, by the time you get to the main sequence, the correlation of activity and rotation period is not as strong.
Thank you.
Is it a similar story for granulation? I guess it's less obvious to me how that would be anything other than a white noise term.
Yeah, what we found when we looked at these sort of effects of different signals is that the spots you can imagine trying to model out with your sort of fancy GPs and whatever, because it's easy to collect data spanning well sampling and rotation period. But the granulation, you can try to observe multiple times within one night. And so what observers have been doing recently is they're saying, oh, let's deal with oscillations by collecting data for, say, 1 to 3 times the p-mode time scale. And that's extremely good at p-modes because there's actually an anti-correlation. And so by integrating over the anti-correlation, you really beat down those p-modes quickly. And you can see in the bottom rows here that oscillations aren't really a problem because we can do that. Granulation is annoying because its time scale is too long for you to want to keep integrating, right? You don't want to integrate for 6 hours, but it's too short for you to, so it's just an annoying time scale. And so one of the reasons that small apertures, like, here we had a set of 6 2.5 meter telescopes, which, you might think, how could they be competitive with designs that have 6 meter telescopes? Well, one of the reasons they're not much worse is because of this granulation issue. They're using longer exposure times that do start to mitigate a little bit of the granulation. And so it does mean that when we were, thinking about what of these architectures are best, before, this architecture 1 looked like it was the worst. But it's a whole lot cheaper than 6 meters. And if you're going to go to, a 15-year survey anyway, I don't know if I might have in another slide, maybe for this afternoon, how you it goes function of time. So granulation is challenging. One thing you can do is within a night, you can leave the star and come back to it. Observers don't really like that because now you have dead time where you're slewing instead of opening your photon. So it's a little work. I'm hoping our next publication will help convince observers, yes, it really is worth giving up your open aperture time to cycle between 3 stars so that you have a larger time gap between your successive exposures to beat down the granulation effectively in one night. So there's some things you can do, but you're right. Ultimately, there's only so much you can do before it's going to be one of the limiting sources. The slide didn't show was for mass. So for lower mass stars, you typically have activity dominated variability, and for higher mass stars, you typically have granulation dominated activity. And what this shows is that once you go above 1 solar mass, even for some of these ambitious architectures with 15-year surveys, you're not able to find Earth analogs in their habitable zone, partially because their habitable zone moved further away, but partially because the granulation is getting worse and not better. And so it may be that our best targets for finding sort of habitable zone planets don't go much more massive than the sun, but are really the K stars up to G stars. The direct imaging people aren't thrilled about that. They like some F stars, but that may be a reality that may have to deal with.
Thank you. All right, let me propose that we take other questions to our continued discussion at 3 p.m. with Eric, and let's thank our speaker again.
Sounds good.
And thank you, everyone.